Hello students, welcome to Sri Jayendra's Rank Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 2 of a unit moving charges and magnetism. Let's begin with today's session. In today's class we are going to discuss about the magnetic field and Lorentz force, that is the that we have already discussed in the class 1 as well. Yes, today we are going to just quickly revise the first class and we will move to the new classes. Let's have a look what magnetic force is acting on a moving charge. Then we used to have this, that F is equals to Q into V cross B, and if I write down the magnitude of this, it would be QVB sine theta, where theta is angle between velocity vector and magnetic field vector. We have discussed already this. Yes, we have discussed certain cases. First case was if V is like this, B is like this. That means V and B both are parallel to each other, the force would be 0. We have discussed the second case where V and B are anti-parallel to each other. This is the case where theta is equals to 180. Again in this case force would be the 0. We have discussed the third case when V and B are perpendicular to each other. Then my charge particle will move in circular path. The charged particle will move in circular path, and we have derived the certain relations based on this. Yes, that what is the radius of the circle, what is the velocity with which it is moving, and all that stuff. Yes, and the last case that we were discussing was that if V and B having certain angle theta, which is an acute one, then this will having a path of helical path would be there, and we have derived a pitch. Yes, a pitch that we call as a distance between two consecutive helix. Yes, we have discussed all this stuff, as well as certain few very logical things that we have discussed is that due to magnetic force, can we change the speed? Can we? Yes, no. Can we change the velocity? Yes, because it changes the direction. Can we change the kinetic energy? Can we change the kinetic energy? No, because speed remains the same. Can we change the momentum? Can we change the momentum? Yes. So we have discussed this many stuff, as well as we have discussed that work done due to, here we are talking about the magnetic forces only. Work done due to magnetic force is always 0. Power delivered due to magnetic force is always 0. So this all are the stuff that we have discussed in previous classes. Yes, now to we want to show the direction of magnetic force using Fleming's left hand rule. So according to the Fleming's left hand rule, if we stretch the thumb and first two fingers in mutually perpendicular directions. Then forefinger points to B, that is the magnetic field. Middle finger points to V, and thumb will represent force acting on charged particle. This is Fleming's left hand rule. Yes. So what does it says? Let's revise it one more time. If we stretch the thumb and first two fingers in mutually perpendicular directions, we are talking about the Fleming's left hand rule. Yes. Then forefinger, that means this finger will points to the B, magnetic field. Middle finger points to the V, and the thumb will represent the force acting on the charged particle. So this is force, this is magnetic field, and this is velocity. So please use your hand, use your left hand. If you are not going to use it, you are not able to see it. So please use it, please use it. Yes, it is the requirement of the situation that you need to use your left hand. Yes, this is the force, this is the magnetic field, and this is the velocity. Thus we can find out the direction of force acting on the charged particle, because we understood that what would be the magnitude. Yes, magnitude can be calculated from this: F is equals to Q into V cross B. But the direction of force can be calculated using Fleming's left hand rule. Yes, there are several other rules too, but we will stick to this only. Yes. So now let's just check it out. Let's just check it out, that find out direction of force acting on charged particle. Let's say first, magnetic field is represented by cross, that means it is inside the plane, and the positive charge plus Q is moving in this direction. This is the velocity. So find it out, the force or the direction of force. Yes, at this point of time we are not interested in magnitude. So if you use your left hand, and if you use it such as the thumb, forefinger, and the middle finger is perpendicular to each other, then use such as magnetic field, that means the forefinger. If you don't understand forefinger, it's your first finger. If your first finger is inside the plane, keep your left hand such as your first finger should represent the magnetic field is inside the plane. Yes, the velocity is in positive x direction. Then if you might observe that your force is in j cap, have you got it? If not, listen to me very carefully one more time. What you need to do is hold your left hand and keep your three fingers ready. It would be a thumb, it would be a first finger, it would be a second finger. First you need to adjust your first finger such as it should be inside the plane. Now what is inside the plane? You are writing in certain book. Yes, your first finger should pierce into the book. Now your second finger should be in the direction of the velocity. If this is the case, then thumb will represent the direction of force. It is something like this. Yes, and that force will be in j cap. Yes, it's in positive y direction. I hope this is clear. Is it? Is it clear? Great. Let's do one more. A magnetic field is inside, and a charged particle plus q is there, and it is moving in negative x direction. It is moving in negative x direction. Now what would be the situation? Again, do the same thing. First finger should be in the direction of the magnetic field. Second finger should be in the direction of the force. Second finger should be in the direction of the motion, sorry. And the thumb will represent the force. Yes. So according to me, it's F should be equals to minus of j cap. That means in negative y direction. I hope this is clear. Okay. Is it clear? Great. If I have been asked the magnitude of force, then it would be Q into V into B, because here theta is equals to 90 degree. How could I get it? This is B, that means K cap, minus of K, because it is inside the plane, and this is V, it is in positive I, and minus of K and positive I both are having perpendicular to each other, so it's a theta is equals to 90 degree, and I can write it's a F is equals to QVB. Same is the case of here, it's a F is equals to QVB. So at this point of time, you just focus to find out the direction. Magnitude can be done very easily. Yes, let's continue this practice. Let's suppose the magnetic field is represented by dot. What is dot? Yes, it is outside the plane. It is outside the plane, and my charged particle plus q is moving in this direction. This is the velocity v. Now you required the force. How should I do this? Let's say this is represented as y. This is represented as x, and the term that is moving out is z. So what is the direction of force? What is the direction of the force? How could you write this? So do the same thing. Yes, hold your first finger such that it should moving out, If it is moving out, then it would be a plus k cap. Yes, it would be moving out, that means it is plus k cap. Your velocity is in x direction, this is the plus I cap. So what do you need to find out? You need to find out I cross k. If you understood using this, it's a v cross b. Yes, F is equals to q into v cross b. If it is the situation, this is I, this is j, this is k. I hope this is clear. Yes, it's a v cross b, it's a I cross k. You are moving in clockwise direction, so that should be force should be in minus of j direction. Yes, this is the value direction of force, sorry. One more example. Let's suppose magnetic field is inside the plane, and charged particle q is moving in the downward direction with velocity v. So hold your first finger such that it represents the magnetic field. Hold your second finger such that it represents the motion. So according to me, force should be in plus I cap, that means positive x direction. This is positive x direction. What was your answer? Is it same? Is it same? Are you sure? Okay, let's do one more thing. Suppose the magnetic field is inside the plane. It is moving in this direction, but now charge is of minus q. So when charge is of minus q, first you need to consider it as positive charge only. Find direction of the force, and at last make rotation of your force vector by an angle of 180 degree. Yes. So what you need to do is consider this as a positive q charge. If it was positive q charge, if it is plus q, then magnetic field inside the plane V is moving downward direction, then the force, it would be in plus I cap. Yes, this was the situation. Now in a reality it is minus q. So what you need to do is you need to rotate your force vector by 180 degree. That means the according to the plus q charge, this should be the direction of the force. Now I need to rotate this vector by 180 degrees, so it should look like in this direction. This is the actual force what I am looking for. This is force on the minus q charge and this is force on the plus q charge. I hope this is clear. This is very easy, very easy. What you need to do when negative charge is there, or when electron is there, they temptfully write it down the electron. They are not mentioning this is negative charge, but we must understand that the charge of electron would be a negative. So if it is negative, what I need to do is that this is minus charge, this is negative charge. First consider it as a positive, find out the direction of force using Fleming's left hand rule, and then at the end reverse the direction of the force or rotate that vector of force by 180 degree. I hope this is clear. Is it clear? Is it? So can it be done? Can it be done? Great. Let's look at one more question. Let's suppose magnetic field is inside the plane. My charge is moving in upward direction, but that charge is of minus of q. So what would be the direction of the force? What would be the direction of force? So if I understood first, force on the plus q charge, hold your left hand such that magnetic field will be inside the plane. First finger inside the plane, second finger in the direction of the motion, the third finger should represent the force. So the force is in minus of I cap. It's a minus x direction, something like this. This is the direction of force. Now in reality I need to apply my force on minus of q. So this is force on minus of q should be as this was the force on plus q. So I need to rotate this by 180 degree. This is force on the minus of q. So my final answer should be equals to plus x direction. That is the force on the minus of q charge will be in the positive x direction. I hope this is clear. Is it clear? Any doubts in this? Anything? Is there any doubt? Is there anything? Yes? No? Anything? No? Great. So let's move further and discuss some very interesting questions. Let's have a look. The question. Let's suppose the situation is that magnetic field has been arranged in this manner. and this is magnetic field B. Now let's suppose we have few charged particles. The trajectory of force, one of the particle is like this, the trajectory of the second particle is like this, the trajectory of the third particle is like this. Let's start working with this. If I have been said that all particles are having same velocity, if all particles are having same velocity and they enters magnetic field perpendicularly, if this particles are if this particles are proton, electron and neutron, identify the particles. So go through the data one more time. What it wants from you guys, that they said that magnetic field has been arranged and three particles has been entered to the region, and magnetic field is perpendicular and all the particles have entered the perpendicular to the magnetic fields. These are the three particles. One of them is proton, another is electron, another is neutron. We need to identify the particles. So how could I come to know that which particle is it? So as a hint, what I understand is that one of them is neutron, and neutron is having no charge. It's a chargeless, yes. As it is having no charge, thus why magnetic force on it is zero. And if magnetic force is zero, its deflection is zero. So it should move straight forward. It should move on a straight line without having any deviation. So third particle should be neutron. I hope you understand this. Yes, great. Now I need to identify which one is proton and which one is electron. How could I get it? Which one is proton and which one is electron? How should I get it? Yes, using Fleming's left-hand rule. Now do the same thing, that magnetic field is inside. It has been thrown like this. This is the velocity. Now find out the direction of the force. If you observe this very carefully, if you understand this, that the magnetic field is inside the plane, velocity is in positive x direction, then the thumb will represent in this direction. The thumb will always represent the direction of positive charge. Yes, so this first charge must be of proton, and if it is of proton, then this must be of electron. I hope these things are clear. Is it clear? So if first charge is of proton, another is of electron, and so on. So you did it. Great job. Do you understand this? Do you understand this? Yes. So can you do this kind of questions? Is it possible for you guys to make it done? Are you sure? Are you sure? Great. So let's just move to the next sessions and to the next question. Let's suppose a magnetic field has been arranged like this, Yes, this is the B. And trajectory or the path traveled by certain particles have been given. Let's say suppose one of the particle is moving like this, some another particle is moving like this, one more particle is moving in this direction, one of the particle is moving in this direction. Yes, let's give them a number. They are the first, second, third and fourth. Yes, first, second, third and fourth. What do you need to identify? You need to identify the particles. Identify the particles, that which one is positively charged, which one is negatively charged, and which one is neutral. So take your time. You are having 30 seconds and do it as soon as possible. Have you done it? Have you? Okay, so let's just conclude it that first particle deviates to right. Yes, first particle deviates to right, and this is possible. This is possible if it is of negatively charged. It is of negatively charged particle. How could I come to know? It's a Fleming's left hand rule, FLH or FLR. Yes, now let's talk about the second particle. As this particle, first particle is moving on the left, the second particle is moving on the right. Sorry, first particle is moving on the right, second particle is moving on the left. So second particle, second particle, where does it going? Where does it going? If you observe this very carefully, it must be entered in this direction. It must be entered in this direction. So this is the magnetic field, this is this, and even the second particle should be of negative charge. Second particle should be of negative charge. How could I come to know? Have a look. This is the direction of B. This is the direction of velocity. So according to this, the force acting in the downward direction for the positive charge, here it is moving upward. That means for the force on is upward for the negative charge. I hope these things are clear. I hope these things are clear. Yes. What about the particle fourth? What about the particle fourth? So fourth particle is having no charge because it is not having any deviation. It is not having any deviation, and when it is not having any deviation, that means it does not have any charge. Now what about the third particle? What about the third particle? Look at this. Look at that. It is moving in this fashion. Yes, it is moving in this fashion. So third particle must be of positively charged. So what you need to do is you need to practice this kind of questions. You need to practice this kind of questions such as this, or or something like this all questions. Yes, this kind of questions is required to be practiced. If it has been practiced thoroughly, you are starting to feel it, and once you can feel it, you can solve this, because these are the questions. And from when we have been in the magnetism, that means there is a club of the magnetism that can be run from the moving charge and magnetism, and in the next session as well, magnetism and matter, and then even for the EMI, it's an electromagnetic induction. Yes, so this is a club. In that, you are going to use your hands to find out the directions, and to find out the potential, and to find out the higher potential, lower potential, and many more things. So you need to use your hand. You need to remember where to use a right hand, where to use a left hand, and every such stuff. So if you remember this, you can do this. If you are not going to remember this, it would be very very difficult to understand, because these are the questions that needs to be done within given time frame. And that is why we need to remember the all the rules, that when to apply left hand rule, when to apply right hand rule, when to apply palm rule, and everything. Yes, but don't worry, I am there to help you. Yes, and we together will make it possible. So let's move it and learn something better. Applications. Those are the different applications. Let's suppose the situation is that this is magnetic field B, and your charge particle enters like this. So if it enters like this, it will just move half of the circle over here and moving back to it. So if you observe this very carefully, this is half of the circle, this is the radius, even this is the radius, and this is the velocity v, which makes an angle of 90 degree with the magnetic field as well. Yes, the particle has entered from this and particle is leaving from this. Yes, there is no change, in the speed, no change in the speed of the particle. Why? Because particle, why is it so? Because magnetic force cannot change the speed of a particle. Yes, there is no change in the radius as well. So we can write like this, it's R is equals to mv by qb. But there is no change in the speed, there is no change in the radius. But what about the time period? Yes, it must have changed. What is it? So we have a time period that is equals to theta into m by q into p. Theta was the angle, that for which angle your particle is within, the magnetic field. Here particle is within the magnetic field for the pi 180 degree, we can say. So this is time period would be equals to pi multiplied by m divided by q into p. This is the time period of the charged particle. Is it clear? Is it clear? Are you sure? Great. This is the first. Let's move certain more typical one. Let's suppose that this is the magnetic field. This is the magnetic field B. This is its boundary, and my charge particle enters such as like this, such that it makes an angle theta over here. It enters at this and leaving like this. We call it as a minor circle. We call this as a minor circle. This is the magnetic field P. Yes. So now I understood. Let's suppose this is v1, this is v2, then this angle, oh sorry, this velocity and this velocity would be the same, that we understood. Yes, this is v1 equals to v2. Radius, the radius would be the same, it's an mv by qb, that we understand. Now what about the time period? It is certain tricky. The time period, how could I get it done? So what you need to understand, first remember the approach. What is the approach? I understood that force and velocity is perpendicular. Now which kind of force is acting? It's a centripetal force. So let's suppose this is the center of the circle, and if it is the center of the circle, this is the direction of the force. So this velocity vector must be at 90 degree. This velocity vector must be at 90 degree to the force. So this is the situation, that this is at 90 degree. If this are at 90 degree, this is at theta. Find out this angle. Let's assume this is y, even this is y, and this is, let's suppose x. So if I understood on this boundary, if I understood, it is very little geometry, please have a focus. It's a theta plus 90 plus y, that should be equals to 180 degree, and from here I can have y is equals to 180 minus 90, which is 90 minus of theta. So this value y is equals to 190 minus theta. Now for this triangle, yes, shall I give it name? No. Great. So this is 2y plus x should be equals to 180 degree, because addition of all the angles of the triangle would be the 180. It's a 2 multiplied by 90 minus of theta plus x should be equals to 180 degree. This is 2 into 90, this is 180. This is the 180 minus of 2 theta plus x is equals to 180 degree. This would gone, and this x should be equals to 2 theta. So this angle, this x, that is of 2 theta. So I could understood that for this 2 theta angle, my charged particle was within the magnetic field. This 2 theta angle, my charged particle was within the field. That means the time period should be equals to 2 theta multiplied by m divided by q into b. Please remember this. This is very essential. Yes, the velocity v1 and v2 would be the same. If this angle has been asked as theta 1, this has been represented as theta 2, this must be the same, that you understand. This is the same. Theta 1 equals to theta 2, v1 equals to v2. This is the minor circle. That means very little part of a circle is within the magnetic field. Is it clear? Is it? Do you understand what things are going on? Do you? Great. Ready for the next? Yes, ready? Great. Let's have a major circle. Let's suppose this is the magnetic field that have been arranged. Now charged particle has entered like this, and it is moving like this. Yes, this is the situation, and it makes an angle theta. It makes an angle theta over here. That this would be the angle theta, or you can understand this would be the angle theta. If here it's a velocity 1, it's a velocity 2, then I must understand that velocity never changes, or speed never changes. Sorry, my mistake. So speed never changes, so this v1 equals to v2. Yes, the radius, it's an mv divided by qb. And time period, how could you get it? So what you need to understand is that, let's suppose this is the velocity vector, this was the velocity vector, this must be the center of the circle. Yes, so here force should be acting because it would be a centripetal force that is acting. So if I observe this very carefully, then this is 90 degree, even this must be 90 degree. If you calculate it as a previous slide, you will have this angle as a 2 theta. But act wisely, because it is not the angle 2 theta which covers the trajectory of your charged particle. The angle which is this angle which will cover the trajectory of your charged particle, and this angle will be equals to 2 pi minus of 2 theta. I hope this is clear. This angle is of 2 pi minus of 2 theta, which covers the trajectory of your charged particle. That means the time period would be equals to 2 pi minus of 2 theta multiplied by m divided by qb. This will cover the trajectory, and this is the time period. Major circle. Yes, I hope this is clear. Is it clear? Is it clear? Are you sure? You want to see it one more time? Take your time. Have a look for the 30 seconds and things will be done. Have a look at this. Have you done with this? Have you? Okay, let's look at this. Take your time, just don't worry. Yes, so will you able to solve this kind of questions? Yes, will you? Is it possible? Let's have a look one of the question. So what they want is that magnetic field has been arranged something like this, and this is the boundary, and they want something like this. Yes, and they have made this angle, they have made this angle as 30 degree. They said from here velocity was v1, from here velocity was v2, v1 equals to v2, v1 greater than v2, v1 less than v2. Our first question from this, and second question, it's a time period of this circle. So what we understand is that, what we understand from this is that magnetic force never changes speed of charged particle, and as it not going to change the speed of the charged particle, v1 would be equals to v2. This is the correct statement. Yes, and this two are the incorrect one. Now time period, as we know this is minor circle, we understand this, that this is the minor circle, and as it is a minor circle, time period could be calculated as 2 theta multiplied by m by qb, that is equals to 2 multiplied by 30 degree multiplied by m by qb, which should be is equals to 60 degree, or pi by 3 multiplied by m divided by qb. That's it, you did it, great job. I hope this is clear. Is it clear? Is it? Great. Ready for the next question? Are you ready? Let's have a look. suppose at a d distance it is a wall, and within this region a magnetic field has been arranged, and let's suppose magnetic field is P. The question is that what should be the value of D such that charge particle Q enters the magnetic field B never hits the wall. This is your requirement, that you need to understand the separation between this wall and this wall, so that if suppose a charged particle, a plus Q is there, it is going to enter over here, never going to hit the wall. So what should be the value of the D? So let's suppose it is going to enter it from here and moving like this. So if this is the situation, let's suppose this is the center of the circle, then this must be the radius of the circle. So if I understand carefully, yes, this is very very simple, that if I can make this separation D which is greater than R, I am all done. Yes, if I can arrange things like this, that if D is greater than R, then I can make sure that charge Q never going to hit the wall. So if D is greater than R, what is R? It's an mv by qb. So if I arrange the value of D, which should be greater than this, that is the D is greater than mv by qb, then it is not going to hit that wall. I hope this is clear. So is it clear? Even certain time they are not going to ask about this. Is the different question, altogether different question. Yes, but same situation. They ask this question, same question, but ask for magnetic field B. Yes, so they said that what should be the value of the magnetic field such that charged particle Q enters the magnetic field B, never hits the wall. So what you need to do is, the condition remains the same. That is the D must be greater than R, that is D must be greater than mv by qb, and according to this B must be greater than mv by q into D. If I am able to do this, it is not going to hit the wall. Is it clear? Now this is the situation where it is not going to hit the wall. But if the separation between these two walls is less than R, that means the less than the radius of the its charged particle's trajectory, what would happen? Let's have a look. That deflection of charged particle, if D is less than R, this is very very critical. This is the situation. If separation between two walls is less than R, this can be only applied if this condition is valid, that if D is less than R, I am going to use this. If it is not, please don't apply it. Just don't rein behind the formulas. Yes, Why I am saying this, that we will discuss later on, but let's look at this. Let's suppose this is the separation D, this is the separation D, and within this region a magnetic field has been arranged. If magnetic field has been arranged, and let's suppose charge particle has entered through this, and after entering through this it is moving like this, and from here it is just leaving the magnetic field. From here it is just leaving the magnetic field. So what you understand, or what you need to understand, is that this would be the radius r of the charged particle, and let's make certain horizontal reference. This is the D. So I can find out the deflection. I can find out the deflection in both the approach. One of the angular deflection, that is with which angle it has been deflected. So I can find out this angle, as well as one of the vertical displacement, that it has entered from here and it is leaving from here. So I can write this as a, let's say, y. So this is the vertical deflection. So what can be done? Let's have a look. So if I observe this triangle, what I can have, it's a sine theta that would be equals to d divided by r. That means it's a d divided by, if I want, I can replace the value of r, which is mv by qb. This is the deflection, or this is the angular deflection. Now according to the y, what is y? I understood that this is r. If it is r, this is r cos theta, here to here. So y is r minus r cos theta. So this is equals to r into bracket 1 minus cos theta. R could be written as mv by qb, and this is equals to 1 minus cos theta. This is the y. This is the deflection of charged particle. Is it clear? Is it? So please understood that this is applicable if d is less than r. If d is not less than r, you need to apply the simple concept. Is it clear? Is it clear? Let's work for the numerical and you will find it. Let's suppose this is the magnetic field, and this d is equals to 2 mv by qb. What they are going to ask is that, let's suppose charged particle is going to enter from here with velocity v. Find out deflection of charged particle q. This is the requirement. So first, what you need to understood is that what is d? It is 2 into mv by qb, which is equals to twice of the radius. Whatever I have derived, it is d. For d less than r, here it is d is greater than r. So when d is greater than r, the situation is particle enters here and particle will be left from here. Yes. So the deflection, or angular deflection, it is of 180 degree. The angular deflection, it is of 180 degree. If you want to find out the vertical deflection, let's understood this is r, this is r. Let's write this as a y. This y could be written as 2r, and this is equals to 2 multiplied by mv by qb. This is vertical deflection. and this is the angular deflection if they have been asked. So you must understand this is for d less than r, because I have seen many students that they made a mistake. They just want that sine theta should be is equals to d by r, put the value of d, put the value of r, and that's it. Yes, but this is not the case, and this cannot be done. Now let's look one more question, that this is the region where magnetic field is there. This is d, and this is mv by qb multiplied by half. Yes, it's mv by 2 qb. A charged particle is entering with a speed v. This charged particle entering with speed v, it is the plus q that enters, and the magnetic field is b. Now they ask that find out deflection of charged particle. So what you need to understand, what is d? It's a mv by 2 qb. What is r? It is mv by qb. So in this case d is less than r. In this case d is less than r, and if d is less than r, I should go with the formula. That means the charged particle enters here and it is going to living from somewhere here. This would be the angular deflection that we call as a sine theta. That would be equals to d by r, and this d, it is equals to mv by 2 qb multiplied by r, which is equals to mv by qb. So this both has gone, and this is equals to sine theta. The sine theta is equals to half. That means this theta is equals to 30 degree. Yes, this is equals to sine theta is equals to half, which is equals to 30 degree. If you want angular displacement, then angular displacement can be written as y is equals to r multiplied by 1 minus of cos theta. As I understand that theta is 30 degree, that is 1 minus cos 30, which should be equals to root 3 by 2. If option permits, it would be an mv by qb into bracket 2 minus of root 3 divided by 2. This is vertical displacement. It is the distance of this situation. I hope this is clear. So is it clear? Is it completely clear, or any doubts left behind? Is there anything which is not clear? Is there anything? No? Great. So please, before applying a rule, always consider that which conditions are there. If condition permits, go with the formula. If condition not permits, go with the concepts. I hope these things are clear. Is it clear? Is it clear? Great. So shall we move further? Shall we? Let's have a look. Let's find it out. New concept. It's a velocity selector. Now what is it? So before I move to the velocity selector, let's just revise certain thing. Initially in the previous class we were discussing about the Lorentz force. What is it? The total force. Why I say total? Because it is for magnetic field as well as it is for electrical field as well. So if charged particle is moving alone in the magnetic field, it is a q into v cross b. If charged particle is moving alone in the electric field, it's a q into e. Sorry, it is at rest. But if charged particle is moving in a region such that a region is having a magnetic field as well as electric field, then motion or the force acting on the charged particle can be calculated using Lorentz force. That force says that this F should be is equals to Q into VB sine theta. I'm talking about the magnitude plus Q into E. I hope these things are clear. Is it clear? So based on this principle, we have a certain device that we call as a velocity selector. Why do we require it? Where do we require it? We are going to discuss it. But before we move to that, let's just look what is velocity selector. So look at this situation. Look at the situation that a positively charged particle is there. It is the positively charged plate, it is the negatively charged plate. So as we understand from electric charge and field first unit, that electric field will be from positively charged plate to negatively charged plate. So this is the direction, in the vertically upward direction. It's an electric field. I have kept magnetic field as represented as a dot. That means magnetic field is outside the plane. Now my charge has been entered through this. My charge has been entered through the region where electric field is there, where even magnetic field is there. So the situation is that if it has been applied two forces, electric force as well as magnetic force, the situation is magnetic force is Q into V into P. Yes, magnetic force is Q into V into P in negative X direction, or negative Y direction, sorry, my mistake. And the electric force is acting in a Q into E in positive Y direction. Yes, it is the situation that magnetic force is acting in a negative Y direction, which is a QVB, and electric force is acting on the Q into E. But this was the case when electric and magnetic fields are perpendicular to each other, and it is also perpendicular to the velocity of the particle. So this is for the velocity selector. I am going to discuss a special case where electric field and magnetic field are perpendicular to each other, as well as they are going to be perpendicular to the velocity of the particle. So they are mutually perpendicular to each other. This would be the situation. E would be in the plus J. Magnetic field, as it is the outside the plane, it is the K cap, and velocity as it is in the I cap. Yes, this was the situation. This is the velocity, this would be the electric field, and this would be the magnetic field. So again, if you are going to apply Fleming's left hand rule, you will have this, that magnetic field or the magnetic force is QVB in which direction? QVB in which direction? Tell me. Yes, it's a minus of Y. And electric force, it is of Q into A in which direction? It is in plus Y direction. So if this is the situation, that this is the electric field, electric force, sorry, this is the magnetic force. If Fe and Fb are equal, suppose it is something like this, then the force on the charge is 0 and it will move undeflected in the field. So if it is something like this, then Fe, which is equals to Qe, Fm is equals to Qvb. This Q and this Q has gone, and this velocity is equals to E by B. And this velocity is known as the velocity selector. So this is the special case. Where magnetic field is there, yes. Charge having a motion, yes. Electric field is there, yes. Even though net force on the charged particle is 0, but for this, V, E and B must be perpendicular to each other. This is the first condition. And the second condition is Fm, that is the value of magnetic force and value of the electric force should be same. If this is the case, and I have entered my charge particle with certain specific velocity, then this is the case where my charge particle will move undeviated. It will move on a straight path. I hope this is clear. Is it clear? Is it clear? Any confusion in this? Is there anything? Any confusion in this? Anything? Anything? No? Are you sure? Okay, great. So let's discuss certain conceptual points. Let's suppose if any region is having electric field and magnetic field, if any region is having electric field and magnetic field, so both the fields are present. So suppose we want that charge is not having any magnetic force. Discuss the possibilities. Yes, the situation is, let's suppose certain region is there and that region is having electric field, that region is having a magnetic field, but what we want, that electric field is there, magnetic field is there, but we want that there should be no magnetic force acting on the charged particle. So how is it possible? So first thing that came into my mind is, let's say charged particle is at rest. If V is equals to 0, then magnetic force would be equals to 0. This is first case. Our second case could be that this is the V, this is the B. That means theta is equals to 0 degree, or this is the V, this is the B. That means theta is equals to 180 degree. Even in this situation, Fm would be equals to 0. So this two possibilities are there. Where it is not having any magnetic force. I hope these things are clear. Is it clear? Yes. Shall we discuss second case study over it? We want that charged particle should be in motion and it is moving in a region having magnetic field and electric field. We want that charged particle should not have any deflection. Is it possible? Go through the question. That what we want that the charged particle should be in motion. That means in the previous case what we have supposed that if charged particle is at rest, magnetic force would be a 0. So here this case could not be there because they clarify it that charged particle must be in motion. Even you cannot say that magnetic field would be a 0 and electric field would be a 0, then there would be a no motion. Yes, but they say that it is moving in a region having magnetic field and electric field. Now what they want that charged particle should not have any deflection. What does it mean? It means they want that net force acting on charged particle would be equals to 0. This is what they require, that net force on the charged particle must be 0. If it is the situation, can we arrange this? What is your answer? Can it be done? Can it be? Yes, it is absolutely possible. First, arrange such this V is perpendicular to E, perpendicular to B. This 3 should be perpendicular to each other. A second situation, that means the second condition for this arrangement is the magnitude of magnetic force and the magnitude of magnetic field will be the equal. If it is the case, then it would be the case of velocity selector. So if we enter my charged particle with this velocity, which is a ratio of electric field, or which is the ratio of the magnitude of electric field to the magnetic field, if I enter my charged particle with this velocity, then it should not have, or it will not have any deflection. That means the F net would be equals to 0. This would be the case. Yes. Is it possible? Yes. These are the logical questions. That can go beyond the boundaries, because when it comes to an logic, you need to understand the complete concept behind it, and then you can reach to it. Is it clear? Is it ready for the one more? Yes. If force on charged particle is 0, discuss the possibilities. Force on the charged particle is 0, discuss the possibilities. What are the situation? First thing is, let's say electric field is equals to 0. So if electric field equals to 0, electric force would be a 0. Let's say magnetic field is 0, that means FB would be 0. So this is the first case when force on the charged particle is 0. When I say force, I mean it would be an electric force plus magnetic force. This is possible. Second possibility is that electric field equals to 0, but magnetic field not equals to 0. So if electric field equals to 0, I can say it's an electric force would be 0, but if magnetic field is not 0, but what I want that FB should be 0. So what I can arrange, that V and B, or it should be something like this. So arrange such that theta should be equals to 0 or theta should be equals to 180 degree. Yes, even though now magnetic field is non-zero, my FB will be equals to 0 because theta is 0, and if theta is 0, theta is equals to 180 degree, then the magnetic force is 0, electric force was already 0. That means this can be done. I hope this is clear. Is it clear? So can you do this kind of logical questions? Yes, this is pure trial error methods. You need to understand each and every aspect. There may be few more possibilities that you may explore, that what else can be done, so that net force could be 0. But that is your task. Please do it, please think over it, and let me know if is there any other alternate possibilities too. I hope these things are clear. Is it clear? Is it any doubts? Any doubts in this? Anything? No? Great. So let's just move to the next. It's a cyclotron. Yes. What is it? And why do we use it? So cyclotron can be used as a future option for power production, and the Department of the Atomic Energy is considering accelerator driven system in which the charged particles are accelerated to very high energies using a machine called cyclotron. So why do we use it? We use it to produce an energy. Why here we are discussing it? Because what we are supposed to do is somewhat related with magnetic field and electric field. So let's have a look what we are going to do and how we are going to do. So what we understand is that cyclotron is a device which is used to accelerate positively charged particles like alpha particles or deuterons to acquire enough energy to carry out nuclear disintegration, etc. Yes. How does it work? How does it work? So look at this. One more thing I want to focus on, that it says cyclotron is a device used to accelerate positively charged particle. So does it mean that negatively charged particle does not work? Does it mean? No, it is not like this. But for a reference or for a smoother functioning, we are using the positively charged particles. There are certain limitations and there are certain requirements that as soon as we are moving further I'm going to discuss it. But please keep this in mind at one of the corner, that does it require only the positively charged particle, or even it can work with the negatively charged particle? Keep this question in your mind and it will be answered shortly. So let's look at the principle. It is based on the fact that the electric field accelerates a charged particle and the magnetic field keeps it revolving in circular orbits of constant frequency. So the situation is look at this, there are two D's kind of thing. This is, can you see this? Yes. No. Yes, this is visible. Yes. Can you see this? This are the two sections that we call as the D's because its shape is English alphabet D. Yes, that's why they are called as the D. So within this D, in this region, crossed fields has been used. While I say cross field, that means electric field is there, even magnetic field is there, which would be perpendicular to each other. Electric field, task of electric field is to accelerate a charged particle, and task of magnetic field is to keep magnetic charge revolving at constant frequency. So what we are supposed to do is, we are having the magnetic poles which can produce a magnetic field for us. These are the D's because this is the top view of the cyclotron. This is the magnetic pole that we have discussed. Yes. How does it work? Let's have a look. Yes, this is the electromagnet, this is the north pole, this is the electromagnet of south pole. Yes, this is the acceleration gap where it can accelerate. Yes, and these are the D's that we have discussed in the previous slide. So D's D1 and D2 are separated by a small gap where source of positively charged particle, oh yes, this is the source of positively charged particle is there, and we have connect this D's with the alternating current source. What alternating current source? They can change the direction, they can change the polarity, something like this. Look at this. This is first, it is the positive half cycle, and next it is the negative half cycle. So they can change the polarity. Let's suppose initially this is of positively charged, then this could be given as a negatively charged, and after certain time their polarity could be changed. So what we are supposed to do is that, let's suppose positively charged particle is there, here the negatively charged d is there. So this positively charged particle is going to enter into this, it is going to be accelerated using a magnetic field. When it will jump to this, this will become negatively charged. How? Because of this polarity. So this will moving like this, and the situation will keep going like this. I hope this is clear. Is it clear? Yes. So what we are supposed to do is, this is the one of them is positively charged and another one is the negatively charged. So the source O produce the positively charged particles for us in the space between the two Ds, and when D1 is negative, let's say this is the D1, this is the D2. When D1 is negative and D2 is positive, the particle is attracted by D1 and charged particle is accelerated towards D1 with increasing speed. So when the particle emerges from the cyclotron through window W, its speed is very large and hence it possesses very high energy. So the situation will keep going. Every time you understand that your radius is increasing, and you understand that radius is equals to mv by qb. So if your radius is increasing, it is your velocity which is increasing, and that's why you use the cyclotron, because you want that high speed particle should be there because it is having a higher amount of energy. I hope this is clear. Yes. So let's just calculate the kinetic energy of the particles, that are accelerated in a cyclotrons. Suppose from the relation we know that R is equals to mv by qb, and from this v max, it's a qbr by m. Kinetic energy of the particle can be given as q square b square r square by 2m. Now one more thing, what is the kinetic energy after one complete revolution? This kinetic energy, or this total kinetic energy, would be equals to 2 times of q square b square r square by 2m. Yes, because one of them is due to d1 and another one is of due to d2. So when they move in one complete revolution, it is twice by each d. I hope this is clear. Is it clear? So this kinetic energy would be equals to q square b square r square by 2m. I hope this is clear. Is it clear? Great. One more thing. This energy can be also calculated as 2 multiplied by q multiplied by v. This v stands for potential difference applied across the cyclotron. Please do remember this. Please do remember this. This is the potential difference applied across the cyclotron that we understood as kinetic energy total would be equals to 2 into q into potential difference. I hope this is clear. Is it clear? Great. Now what are the limitations of a cyclotron? What are the limitations? What we understood, it's a cyclotron cannot accelerate the particles to velocity as high as comparable to velocity of light. This is first of the limitation. Why is it so? Because at this velocities the mass m of the particle increases with increasing velocity. Why? According to this relation, yes, given by Einstein, it's an m is equals to m naught upon 1 minus v square by c square. So if its velocity go beyond certain limit, or it is comparable to velocity of light, its mass is going to increase. And if its mass is going to increase, there are certain restrictions on that, because r is equals to mv by qb, and this t, that means the time period of the alternating source can be changed, and as it is changed, it is not in sync It is not in sync with the D's and the whole operations will be vanished. So this is biggest limitation. Uses of cyclotron. It is used to energize the particles accelerated by cyclotron are used to bombard nuclei and study the resulting nuclear reactions. In modern physics, you are going to discuss and you are going to study the nuclear fission, nuclear fusion, where to bombard the radioactive materials, to bombard the certain materials, we use the cyclotron. It is also used to implant ions into solids and modify their properties or even synthesize the new materials. It is used in hospitals to produce artificial radioactive substance which can be used in diagnosis and treatments. Is it clear? Is it clear? Now, the question that was in your mind, that can I use negative charged particles? Can I use electrons? Yes. You can use every charged particle, but their mass should be comparable to proton, at least to proton. Yes, if your mass is very less, you cannot use it. So it is the requirement of mass, not the requirement of charge. You can use both charges, that is the both nature of charges. You can use the positive charge, you can use a negative charge. There is no issue in that. I hope these things are clear. Let's look at the certain MCQs. Cyclotron is a device by which high frequency wave can be generated. Positively charged ion can be accelerated to high energy. Yes, no high frequency waves. Electrons can be accelerated. Electrons cannot be accelerated due to its mass. This limitation is due to its mass, not due to negative charge. Please remember this. Electrons cannot be accelerated using a cyclotron due to its mass, not due to its negative charge. Let's suppose, assume that this is not possible. We are talking a very hypothetical, but please assume that suppose electrons are having a mass same as the protons. Can we use electrons? Yes, we can use it in cyclotron. Yes, I hope this is clear. Now, second, the cyclotron is used to accelerate. Cyclotron is used to accelerate. Yes, it is used to accelerate proton. It is used to accelerate alpha particles. So this is the correct answer. Next, in a cyclotron, an electric field is used to accelerate a charged particle, and magnetic field is used to keep it moving or keep it rotating. Yes, so is it clear? Any doubts? Any doubts on this? No? Yes, so let's just wind it up this session over here. Probably this is the biggest session up till now, what we have discussed. Yes, so this is a theoretical plus conceptual questions of magnetic forces and Lorentz force. Please revise this lecture as well as part 1 of this session. Yes, because this is the beginning of the moving magnetism technicality. Yes, please practice a lot. Please practice certain questions that can use the Fleming's left hand rule, because once you have a grip over it, you can do it anywhere, you can do it at any time, because that has been delivered to your subconscious mind. This is requirement. Yes, so please practice as many questions as possible. Thank you. Have a good day. Take care.